Okay, extreme values and saddle points. So extreme values of f(x, y) occur at either boundary points of domain or domain of f, or at critical points of f. Critical points are where f(x) equals x, fy equals 0, or points where fx or fy fails to exist, We basically only deal with the main thing being the fx equals fy equals 0 here. And the second derivative test is then used at the critical points to find out exactly what we're looking at. So second, basically, in these conditions, fxx less than is negative, and fxx fyy minus fxy squared. Yeah, I mean, you can call this the discriminant, or whatever we want to call it. I'm just going to use this format because I think you might as well not overload. I don't know. You can look in different ways representing this, but this is like the representation. These are these second partial derivatives as noted in the format. Product of two of them here, and then the square of one singular one, greater than 0. That's a local maximum. If fxx is positive and that's positive, that's thingy, you got a minimum. Then a saddle point is where it's less than this. Just this thing is negative. The discriminant, as some people as it can be referred to, and if the discriminant equals 0, then you have a meet inconclusive test. You can't really find it this way then. So yeah, you just have to remember that. Now to perform. But that's the main thing that's really new here. Oh yeah, and you have to use some old algebra tricks sometimes to solve these, depending on how it works. But you're solving basically a system of equations, basically. So you have x squared plus xy plus y squared plus 3x minus 3y plus 4. It's your function. Fx, fy are given. You have to derive them as such, and you're trying to find in all these problems. Are just finding the minimum, the local minima, local maxima, and saddle points. Basically, that's all you have to do for 4 problems, but it can take some getting used to. So you set these equal to 0, and that's when I try to explain it properly here. So I solve for y in the first equation, and I get formula number 3 basically. Then 3 into 2, I get eventually x equals negative 3. Then I plug x equals negative 3 into the second equation here. And get y equals 3. Yeah, I did it the plug-in where you find it in one function, then plug that into the other function. Basically, that's what I used. Then you solve for the other value once you solve, basically. So it's like a normal one method. You could technically just subtract by double this product, and you'd eliminate x and just have y in terms of y, basically. But regardless, sometimes you have to use what you can, depending on the situation. This one would be easily solved many ways, basically, as linear equations. The critical point is negative 3 from x and 3 from y. That's what it is. That's only one. It's only solution. So we have 2 fxx2, foy equals 2, and fxy equals 1. This is regardless, so we don't have to do any plug. You'd have to plug in each point normally, but there's only one point, and there's no x or y values, so it's very simple. In effect, the first 2 problems are going to be relatively quick, at least to understand. The last 2 might be a little bit of a doozy, at least with having to do a lot of work. And you basically plug in, so it's 2 times 2 minus 1 squared. Because you plug in that formula and you get this discriminant is equal to 3, which is positive, and f of x is greater than 0, it's 2. So it's local minimum at negative 3, 3, and the local minimum is value of negative 5. You just plug in the point into the function, the original function. So now we have x squared plus xy plus 3x plus 2y plus 5. And you get these equations. So in this case, you definitely want to do it because you already have x plus 2 equals 0, so it's x equals negative 2. Then you substitute that into the first equation to get 2 times negative 2 plus y plus 3 equals 0, and you eventually get y equals 1. So the critical point is just negative 2, 1, just one critical point this time again. And again, you don't have to do, you have to do like the last one. You find your second partial derivatives You solve for that and you get -1, and that's less than 0, so it's negative discriminant, and that means a saddle point by default. I must always say saddle point at -2, 1, or you could say f of -2, 1, the point -2, 1 is a saddle point. That's all you do. Critical points. Oh, it's another one. Okay, sorry, it's out of order. So here we have 2 more. We did 2. Now it's time for longer ones like this. F of xy equals x cubed plus 3xy squared minus 15x plus y cubed minus 15y. Okay, the partial derivatives are going to be a little bit need more work done. So they're not hard to get at least this one. They're not hard to do, but they're not going to be as easy to solve. I suggest you actually subtract them this time to make it easier. So you subtract the 2 equations, and you get 3x squared minus 6xy equals 0, which means you can divide out 3x, so you get 3x and x minus times x minus 2y equals 0. It means 3x equals 0, x minus 2y equals 0, and x equals 0, or x equals 2y is what that simplifies down to. So for x equals 0, you get y equals plus or minus square root of 5. Sound pretty good? Then for x equals 2y, you solve for y and you will get y squared equals 1 eventually, so y is equal to positive minus or -1. And that means that y equals 1, x equals 2, and y equals -1, x equals -2 are other solutions. So we technically have 4 points, but we basically solve it like we have 3. And you'll see we can do that. I mean, you could do it individually, but you'll get the same result for one of them, basically. And that's because the plus or minus square root of 5. You'll see what happens. Sometimes you do it to make it a little bit easier. You could do this individually, though. You could make it 4 points. It is 4 points, but just 0, it shares the same x coordinate as a different y coordinate. So the partial derivatives are the second order partial derivatives are 6x, 6y, and 6x plus 6y. Right. So at 0 plus or minus square root of 5, I think one of these is going to be oh god, this will figure this out. So at 0, positive, negative. That'll be -2. Okay, so there we have it. Okay. This takes up a lot of work. A lot of space. I help by scribbling some things out. At 0 plus or minus square root of 5, this becomes 6 times 0 times the product of 6 times 0 plus 6 times plus or minus square root of 5 minus 6 times plus or minus square root of 5 squared. So in the end, this simplifies down to 0 times something. So that's just 0. Subtracting 36 is 6, so you take the square. 6 plus or minus, this is basically plus or minus 6 square root of 5 times plus or minus 6 square root of 5. When you do a square, you eliminate the negative, so both the positive and negative will be the same. So in the end, it's 36 times 5, because it's 36 times 6 is 36, and negative square root of 5 times negative square root of 5 will be square root of 5, just 5, and the same thing was positive. So it ends up with, you get negative 180, basically 0 minus 180, and that's negative. So that'll be a saddle point. Both positive or negative y values will lead to a saddle point. Yeah, and the function at 0 plus minus square root of 5 is saddle point. You see it. At 2, 1, you plug in the same way as before. A little bit easier though. Plug in this value. 12 times 18 minus 36 will obviously lead to, again, it gets to 180, and that's positive. So it's positive, and fxx is positive, because 6 times 2. So it's, 2 is your 6 times, because 2, 1, so x is equal to 2 here. So 6 times x, that's what gives you. So it's a minimum, and then you plug in, you get negative 30. Next one's going to be a maximum, and we'll see this by basically you end up with, again, a positive value for this discriminant. And f(x)(x) is negative, because it's negative 2 times 6, and it's negative 12, which is negative. It's less than 0. So it means that local maxima, yeah, no, that's the local maximum. Yeah, it's 30, and the other one is the local minimum. And so you have a saddle point, local minimum, and local maximum. Yeah. And then the last one, you have function. Okay, it's not too terrible. It doesn't look like it at least. 4xy minus x for force minus y force. So take the derivatives and yeah, cubes. So you solve. Well, at least this time you can easily solve for y and x. Kind of. You can take 4y minus 4x cubed equals 0, and you basically get 4y equals 4x cubed, and that means y equals x cubed because you divide by 4. No. So y equals x cubed can be substituted into that equation, and you get an expression for x as well, involving only x. So you get 4x minus 4x to the 9th power because x cubed is x to the 9th power, and that's equal to 0. So I think there's another way to solve it, but like in this case I did it like this. I think there's another, but since it works out, I just did it this way. I don't know how often, don't know if it's the most popular way, but I did it. So 4x times 1 minus x to the 8th power will be equal to 0. So x equals 0, or 1 minus x to the 8th equals 0. I think you can technically split this up, but I said x to the 8th power equals 1. Now, 1 is a very simple number. You could do this in your head. You could also do it with a calculator, because how this simple expression is, but it'll be plus or minus 1. Like square root of 1 is plus or minus 1, fourth root. So it's the 8th root we basically take of 1, because that'll be x. So it's plus or minus 1. So you have y equals x cubed every time. So x equals 0 means that it's y equals 0, x equals 1, y equals 1, and x equals negative 1, y equals negative 1. So those are your critical points, and you plug in. Okay, first we have to find the partial derivatives, the second order. And you get, well, and I've created a general expression this one time since we definitely need one for this. 144x squared y squared minus 16, just from plugging it in. Then you use this for each one to solve at each point, and it doesn't take long. You have a negative discriminant. So that means saddle point. Doesn't matter what f(x)(x) is, even if it's 0. You don't have much with it. At 1, 1, you get a positive value and a negative f(x)(x). So a local maximum with a value of 2, and the same, and negative 1 gives you another local minimum. Oh no, it should be maximum, I misspoke that. But this is a local maximum, ignore that. Same value as 2, so it should make sense. But yeah, something's going on. It makes some sense because the function is like this. You know, it's force power, so I assume there's some stuff going on. You have a lot of zeros in just the normal function itself. So I assume stuff's going on. And those each could be local minimum maximum those. So yeah. I'm surprised it only has this many points. Oh. But that concludes that pretty much, yeah. Remember, this should be a maximum, so there's both critical points give you a local maximum, and you have a saddle point for that one.